We are going to start the session of Isogeny Signatures. So we have the first paper for the session by Alexander Karenin. It's a collaboration work with Otto Hyens, Elena Krishanova, Peter Kutas, and Sina Skoffer. And the paper is Constantine lattice reduction in dimension 4 with application to ski sign. So let's welcome the speaker.
Thank you very much for the introduction. Let's get started. Why do we care about ski sign? Well, first of all, ski sign is a digital signature algorithm which is post-quantum, and it has a very short public keys and signatures. It also made its way into a second round of NIST PQC competition, and that's precisely why we think that this particular scheme is interesting to... Oh, sorry. I guess something went wrong with my pult. Sorry, minor technical issues. It goes backward, but it does not go forward. Sorry. Yes. So we would like this algorithm to be constant time for it to be more secure. And what do we have so far? We have so far an implementation of a certain subroutine of this scheme, namely the Karnacki algorithm. But in terms of the main and heaviest part of the algorithm, that is the scheme, that is the KLPT algorithm, we don't quite have any significant progress so far. However, just a few days ago, we had some paper regarding the arithmetics in constant time, which is specific to this scheme. However, the reaction of community is yet to be presented. So, ski in ski sign stands for short quaternion isogenies. I know it may scare someone in this room, but isogenies can be dealt with by the means of ideals, and we are dealing with ideals by the means of lattices, a much easier object to comprehend. So, and in lattices, what do we like to get? Is to get short lattice vectors. So we just forget about Q and I in ski sign and focus on short. So in terms of where do we position ourselves within the ski sign scheme, we are basically in the quaternions module of the ski sign and also in the big integer arithmetics, which we would like to make a constant time. So, what the lattices are? First of all, that's the main object we're dealing with in this particular work. And it's a discrete additive subgroup of a real vector space endowed with a sum vector product. In ski sign, we work with four-dimensional lattices. That is, in every lattice basis we're dealing with, there are four basis vectors. And each vector of a lattice can be represented as a z-linear combination of these vectors. That is the integral combination. Then our inner product is derived from the quaternion side, but again it's given us explicitly and can be found on the formula given on the slide. Now the next two quantities we are introducing are crucial to our algorithms because typical algorithms on lattices, their runtimes depend on the two following qualities. The first one is a gram matrix, which encodes the geometry of a given basis and therefore the geometry of a lattice. And the second quantity is a determinant of a lattice, which controls how sparse a lattice appears within the vector space it lives in. Yes, so we look at the lattices by the means of their bases. Their bases are the ways to represent a lattice in a compact form. Each lattice has an infinite amount of bases, some of which are bad, just as a red ones on the slide. They are skewed, these vectors are rather long, and it's not nice to work with such vectors. And then we have good bases, the green ones. They are fairly orthogonal, and they are rather short. So we would like to work with green bases. Again, our lattices we encounter within the CHES sign are not typical. In lattice cryptography, we are usually dealing with a large number of dimensions, potentially thousands, whereas here we are dealing with dimension 4. In lattice crypto, we are usually dealing with Euclidean inner product, and the inner product in CHES sign is rather unique, I would say. In lattice-based crypto, we're dealing with relatively small integer sizes, usually fitting into 64 bits for most of the applications. And in CHES sign, we have large integers, hundreds, but potentially thousands of bits. In lattice crypto, we usually would like our algorithms, their performance to scale well as the dimension of a lattice grows. But here in CHES sign, the dimension is fixed, and we only need fast and secure reduction. But what exactly is secure? Well, secure in our work means constant time implementation. We're not talking about masking so far. We only want all the algorithms to run in time independent of a lattice. In order to do so, we first need to assume that we have some basic arithmetics and comparisons made in constant time, implemented in constant time. And we need that for all our inputs to be bounded in their bit size, because otherwise we would be able to come up with a constant time lattice reduction algorithm. What exactly do we protect? If a determinant of a lattice grows, we are dealing with larger integers, things get messy, and the runtime of typical lattice reduction algorithms, it grows. As the geometry of lattice worsens, we need to perform more steps just for us to make a basis better. Just as an analogy of earphones put into your pockets, the longer the earphones are in your pocket, the messier they get. If we're not cautious, we may leak both the geometry and the sparsity of our lattices, which may lead to an attack versus CHES sign. These values should be private, and the runtimes of our algorithms should be independent of these values. So how do we get good bases out of the bad ones in the first place? We may utilize a celebrated LLL algorithm. LLL stands for Lenstra loads, and it was introduced in the early 80s. So how does it proceed? It iterates through consequent pairs of basis vectors. Then it does something that is called a size reduction, more on that later. Then it checks a certain condition called the LLL condition, which basically controls whether two consequent basis vectors are reduced in some sense. And if they are not, we perform swap and then make a step back in our outer loop. Now, what issues do we have with this particular algorithm? The first issue can be found on the second line. We don't know what size reduction is so far, and we don't know if it's constant time. The second issue is on the line 3. We can see here a conditional branching, and that's a big no-no for constant time algorithm. And the line 5, it's a non-trivial branching within our algorithm. Again, because line 3 may not be triggered, so we wouldn't need to make a step back. Now let's address these 3 caveats, starting with a size reduction. Well, what is a size reduction? Here on the figure you can see a nasty basis. It's really skewed, and we would like to get a better basis than this one. So what do? We first project the first vector onto the zeroth one and get the projection mu of around 1.7. Now we would like to substitute 1.7 B0s from B1. but we cannot do so because if we don't round this real number to some integer, we will land outside of a lattice. So we basically just round the projection and substitute two B0s from B1. And as you can see, the basis is somewhat better, I guess. It's still not the best basis we can get in the wild, but it definitely looks better. Now, from the pseudocode of this algorithm, generalized to the lattices of dimension 4, we can see that this algorithm is constant time as soon as all our arithmetics is made in constant time. All the bounds of the number of loops are bounded with a constant, and every other computations are just basic arithmetics. So we have no problem on the line 2. Let's now resolve the problems with lines 3 and 4. Unfortunately, it's impossible. Unless we change the way the very LLL algorithm works, we need to rework the workflow, the main idea behind this algorithm. So in order to do so, we first need to introduce something called Lagrange reduction. So the Lagrange reduction works in 2 dimensions, and it gets you basically the best possible basis one could ask for in 2 dimensions. It ensures the the conditions given on the slide, and it proceeds as follows. It receives 2 basis vectors, its size reduces them, and then swaps them. Then these steps are continued until our basis is Lagrange reduced. That is the best one we could obtain. This routine will be the core routine for our algorithm that would be constant time. However, there is a small issue with this algorithm. It's not constant time. Ouch. But can we make this algorithm constant time? And the answer is yes. However, we would have to keep up with the fact that our Lagrange reduction may fail with some small probability. By failure, I mean we won't get a Lagrange reduction, a Lagrange reduced basis. So what do we do here? We just bound the number of swaps and size reductions artificially with some predicted value. In order to predict this value, I send you to the Valais result from 1991. And now we are ready to present the constant time lattice reduction algorithm. So basically, what do we do here is that we proceed in tours with the BKZ2 algorithm. Here we as well consider a pair of consequent basis vectors. Then we make TBKZ tours. That number is to be determined later. And then we, for each pair of consequent basis vectors, we do T Lagrange iterations of the Lagrange algorithm. And basically, we proceed on with this framework. Now about the values of the numbers I have mentioned. If we get this many BKZ tours, the number of the iterations of the outer loop, and if we get, that many Lagrange iterations, then what we can do is we can basically get a bound on the norm of the first basis vector. And that's exactly what we needed for ski-sign, to output short vectors for them to be utilized later on within the scheme. And as you can see, the runtimes of our algorithm relies on the gram matrix and the lattice determinant as predicted. And once we fix an upper bound on these values, basically what we get is a constant time algorithm, lattice reduction algorithm. But the mathematics says that the number of BKZ tours is tens to hundreds, and Lagrange iterations are thousands. That's an enormous number. However, in theory, as can be seen from a slide, we don't need that many iterations. Here you can see, looking at the blue line, which corresponds to the number of BKZ tours equal to 4, that at around 10 Lagrange iterations, we may ensure that our algorithm does not fail. And by failure, I mean, not getting the first vector within the prescribed bound. Now let us benchmark our algorithm against the algorithm that is used as of now in SkiSign. Here what you can see is the runtimes in terms of gigacycles. The constant time algorithm that was introduced in 2022 by the SkiSign team with non-constant time non-constant time arithmetics is actually faster than we. Of course, constant time implementations come with such a caveat as it just runs longer. We cannot quite do anything about it. It happens basically everywhere. However, if we produce a certain trick, I guess the buttons here just map randomly. Yes. However, if we introduce a certain trick, I won't delve into details because I don't have time for that. We're actually competitive within the old LLL algorithm. However, that information is valid for the first round SkiSign submission. If we go second round, where the SkiSign team has introduced floating point arithmetics into their algorithms, we are way slower than the state of the art. So I guess maybe if someone has a constant time implementation of floating point in arithmetics, I'll be happy to reach out to you because that's definitely what we need. So, okay, mathematically we are constant time, but what happens in practice? Here on the figure, you can see the runtimes in gigacycles of both our algorithm, the orange line, and the competitors, the green line, against the determinants of lattices. As you can see, the green line depends on the determinant of a lattice as predicted, and our orange line is flat. So our runtimes do not depend on the determinant of a lattice. We also made a statistical test using the RTLF tool. And basically it said that we are constant time and proved it statistically. Now let us conclude the talk with the results and open questions. Now we have a constant time implementation for an LLL algorithm that utilized within every flavor of SkiSign. We have mathematical proofs that our algorithm is constant time, and we have statistical evidence that we are constant time. Now to the open questions. Actually, what hits our performance is inefficacy of our arithmetics. We spend about 90% of our time on GCD because we use rational arithmetics instead of floating point one. So maybe one could speed up the GCD, or maybe we could even switch to a floating point arithmetic if it's possible in principle for constant time algorithms. Also, we'd like to trade off failures for iteration numbers because actually we wouldn't like to run as many BKZ tours, as many Lagrange reduction swaps. Maybe we can lower these numbers and find certain trade-offs, so maybe we fail with some probability, but we are actually faster. Our algorithm was implemented in C and is publicly available on GitHub, and our article is also open and publicly available on ePrint. Thank you very much for your attention. I'm open for your questions.
Thank you very much, Alexander. So really nice talk. Okay, there is any question from the audience? Okay, good.
Thank you for your talk. What can you do if there is a failure? Do you have to restart with a different key, or can you reorder the basis vectors to try again, or what do you do?
Actually, fun fact about ski sign, even perfectly implemented LLA algorithm may fail. I mean, it will still output a vector we are looking for, but then ski sign may reject it due to reasons outside of the lattice world. And that's why, yeah, we'll just construct another lattice and proceed
So
further.
it's just to bury the failure in the other failures.
Yes, and actually, if our algorithm fails, it may still output a somewhat short vector, which may suffice for ski sign.
Thank you.
Any other questions? No? You look so excited. Yeah, I have one question. So this, all the results are completely focused on ski sign 1. So do you have any signs how will be the speed off or slow down if you include this or extend this to ski sign version 2?
You see, it's quite a hard question. We have compared our implementation of LLL algorithm alone versus ski sign that uses non-constant time arithmetics and very slower. So our LLL algorithm alone is slower than the entire scheme. However, it's not a fair comparison because if we are using constant time arithmetics, then the ski sign itself, the other modules, should use constant time arithmetics as well. And in that case, so far we cannot compare these two instances of ski sign fairly. But of course, the heat as of now would be significant, so we definitely need to master this technology.
Okay, thank you. Any other questions? We are just two talks in this session, so if you can ask whatever. If not, well, I can drop another one. So, which is the probability for failing? Is it the same for each level, or is it different?
Actually, the probability of failure of our BKZ2 algorithm depends on the number of Lagrange iterations, and it may be predicted by us. So far, we only have, let's say, statistical and experimental data where we were able to find for each level the parameters at which we don't fail in practice. In theory, we also have an upper bound for a failure probability. However, it's rather loose, so I don't think it's reminiscent of a practice whatsoever. That's why my answer would be we can only answer if we make enough experiments.
Okay, this is good. That's a fair answer. So, no more questions? If not, let's thank the speaker again. Thank you, Alexander.
Thank you.
Let's go with the second talk. Ready? Yeah, okay. So this talk is presented by Isaac Andres Canales Martinez. So there is a bunch of people there. So, but it's Felix Cidro Rodriguez, Decio Gazzoni, Cora H, Jorge Chavez, Francisco Rodriguez, Julio Lopez, Michael Scott, and I think that's all. So the paper is, well, the title of the paper is Generation of a Finite Field Arithmetic for Cortex M4 with ECDH and ski sign applications. So let's welcome the speaker.
Thank you very much for the introduction, and thank you everyone for being here. Okay, so let's get started. But first of all, I would like to start this talk with a short story. Once upon a time, there was a group of really brave cryptographers, and they learned how to ski in a beautiful one-dimensional isogeny graph. Particularly, they did so in the x86 slope. And even though they were successful, there was one caveat. I don't want to say a problem, but just a small remark. And that is that maybe the slope was not very steep because they were skiing quite fast. Well, relatively fast if you compare it to, going jogging in in the lattice valleys or going for a hike in the forest of code-based schemes. So yeah, they were just a bit slow. Soon after these events, another team of courageous cryptographers decided that they wanted to ski faster. And they wanted to do it both on the same slope as before, and also on the larger and small arm slopes. So on they went, these cryptographers, with this quest. And if you're curious to learn about the outcome of this story, then I highly suggest you that you attend another ski sign related talk that will be happening Thursday at the end of the session of the conference, which is titled "Optimize One-Dimensional Ski Sign Verification on Intel and Cortex M4." Anyways, spoiler alert, they succeeded. And I will give you or I will be discussing here one of the parts in which they focused in order to achieve this goal. And particularly that one way in which you can ski faster is to do finite field arithmetic faster. And this is practically the focus of this talk. All right, so if you have attended some of the other talks, particularly today in the plenary room, at the end of the talk, it was mentioned that performing finite field arithmetic is quite important if you want to speed up FHE schemes. Also during the tutorials, Kambisher mentioned that also focusing on speeding up the implementation of finite field arithmetic will in the end yield faster schemes or implementations in general. So practically finite field arithmetic is one of those very foundational building blocks in many cryptographic schemes. And if we want to optimize our implementations, there are many factors that play a role in this. Particularly, you can take a look at the characteristic of the finite field, which reduction strategy you are using to do this, how you represent elements, just to name a few. And given that this is a very important part of implementations of cryptographic algorithms, it's no surprise that a lot of effort has been put into making finite field arithmetic fast. And of relevance to this talk is the work that a lot of people have put into creating what are called generators of portable finite field arithmetic code. Among these, one can mention Fiat Crypto, which particularly was used for the reference implementation of the round one submission of SkiSign. And another one that is relevant to this talk is Moderate. Moderate was the one taken by SkiSign for the round two implementation in the round two reference implementation of the scheme. Now, let's assume that we want to embark on a journey to implementing finite field arithmetic. We have several strategies, if you allow me to call it that way. The first one is we can just take generic code. Imagine just take GMP, because we're dealing here with multi-precision integers. And then we use this to implement, addition, multiplication, and then perform the reduction. So if you decide to go this route, you're practically already giving up on potential optimizations that we may get from these considerations that I mentioned before. Now, on the other side of the spectrum, we can do all the way down and start writing assembly code all on our own. This yields definitely the fastest implementations that you can have. However, the drawback is that if we want agility, meaning if we want to maybe later write code for another prime, parameters change, we need to implement more things, then this is quite slow. So agility is lost a bit. What happens in the middle of the spectrum? So one of the players or one of the strategies that we can take is actually using one of those generators that I was mentioning before. These, in general, what they do is that they include some optimizations that are based on the prime, and they also provide some agility. There is one, let's say, something that is quite close to this one, and it's actually the focus of this work, and is to do code generators attacking, or not attacking, but targeting a certain platform. In this way, we get close to the assembly part that I'm showing here. We get agility, They are clearly not the fastest compared to handwritten assembly, but we get, let's say, fast enough. All right, so if you remember in the title of this talk, we have the ARM Cortex-M4 keyword in there, so I will quickly just go through what the Cortex-M4 is. So the Cortex-M4 corresponds to a type of processors following the M-profile architecture by ARM. And well, this is nothing but the market leader for embedded devices, and you can find them in things like IoT, smart devices, aerospace, many places. These processors implemented the ARM v7-EM instruction set. They have a 32-bit word size, and they are comprised of 16 registers, but only 14 of them are general purpose. So I will just mention here that we have 14 registers. They are in order single-use microarchitecture, and most of the instructions that we have available for us executing one clock cycle, with the main exception, well, not main exception, but important for us, are instructions that load and save to memory. These ones can be pipelined, and then we can get a throughput that gets closer to the one instruction per cycle, but yeah, it depends on how they are pipelined in the processor. Also, we have something that are called DSP extensions. I think it stands for, if I remember correctly, it stands for Digital Signature Processing Extensions. And particularly here, we can find some instructions that are well suited for performing finite field arithmetic. Now, when we decided to focus on creating a generator of code for finite field arithmetic targeting the Cortex-M4, we found some challenges. This is not a challenge, of course. This is just one of the, if not the only instruction that is relevant for our use case, which is the UMAL instruction. It stands for unsigned multiply accumulate long. And it computes this thing that you see here. So you take 32-bit integers. Of course, when you multiply, you get a 64-bit integer, and adds these two other values, and then the whole result, which is 64-bit, is stored in, let's say, 2 registers with the high and low part. And if you notice, it's quite powerful because we are practically performing 3 arithmetic operations, meaning 1 multiplication and 2 additions in only 1 clock cycle. So this is very powerful when we work on the Cortex-M4. The problem, or one of the problems, is that this instruction is not directly accessible through C code. The compiler is the one that will decide in the end whether it will be used in the compiled version of the code or not. So we don't have much control over this. Another thing that we need to think about very carefully when doing this is what I mentioned before, how you represent elements. And the long story short, here we have 2 options. We can go for a saturated representation, in which we represent a multi-word integers taking several words, and then we use all the bytes in each word to actually represent the number. Or we have what is called the unsaturated representation, in which we leave some bits unused in each word, and then we can just, this allows us practically to postpone reduction for later, because we can somehow use that extra space that we have available for us. We can do some sort of parallelism, but in this case, it doesn't really matter. So, given these challenges, we decided that the best strategy we can have is to use C with inline assembly macros. Having the inline assembly macros will give us direct access to these, but still using I'm going to call it a high-level language, because I consider C to be a bit of a higher-level language. And yeah, so after this, we decided again to create our library, and then I will start mentioning some of our contributions in this regard, and then we will be discussing, or I will be showing you a bit of results of the application of our code generator. First of all, we made we optimized, or we paid careful attention in the multiplication strategy. Particularly, we focused on minimizing certain instructions, namely the number of loads and stores that we use to perform multiplication. As I was mentioning before, loads and stores are the ones that significantly can increase the time we spend in doing arithmetic. And the second part that we try to minimize was the overhead of function calls and returns. Now, when it comes to the first part, the main contribution is that we propose a new hybrid operand caching multiplication. Previous work was able to use the block size 3, and some others were able to use a block size of 4, but with this, the number of operations increased. So what we did is we were able to increase from 3 to 4, keeping practically the same number of operations as with 3. I will not go into the details of what operand caching is, but if you are curious, you can take a look at the paper. We can discuss later, but due to lack of time, I'm just going to say that it's a new approach to hybrid operand caching. Now, when it comes to the second point, which is overhead of functions, well, I think this is nothing new, but we can just play a bit with the inlining functionality in C, so that functions are not actually seen by linked against each other, but they are introduced there, and then we can reduce some of the overhead in the implementation. With this, we also can see that when we want to square, it's just a special case of multiplication. When we square, we take an input x, and we just compute x times x. And if you remember from primary school years, you know that we can multiply numbers. We have like some sort of rhombus that we start adding together. So if you take a look at x times x, you will notice that half of the values are practically computed twice. So that's so what we can do is just compute them once, then multiply by 2, and well, add together, multiply by 2. And that way, or with that idea in mind, we obtain that squaring is more or less half of the cost that we have for multiplication. The second, let's say, bit of contribution is on the modular reduction strategy, particularly when it comes to pseudo-Mersenne primes, which are primes that have this form. We made a generalization of an efficient reduction strategy. And again, due to time constraints, I'm not going to present the idea behind it. But yeah, we just formally proved that the new strategy that we present holds. It's mathematically secure, let's say, or there are no errors in the computation, and this allowed us to reduce times. And having this, we actually present what we called M4 Modarith, and this is a library that is based on the library called Modarith, developed by Michael Scott. This is a finite field code generator. The code that it outputs is C, and it is targeting the ARM Cortex M4. It uses a saturated representation, since the size of the word for these processors is 32 bits, then the radix is 2 to 32, and we have 2 reduction strategies. The first one is pseudo-Mersenne, which is practically what I showed in the previous slide, and then we have the more general Montgomery reduction. Before I go into this, I would like to mention that once we had this generator ready, then we decided, okay, we want to try it out in the wild and see how it performs compared to other generators. And we chose two applications. The first one is elliptic curve Diffie-Hellman, particularly as specified in the memorandum RFC 7748. So this uses a Montgomery curve, and then it computes the shared secret using X-only arithmetic. Particularly, it uses what is called the Montgomery ladder, and it requires only finite field operations. Compared to Modarith, which is the general C code generator by Mike, we found that we were 2.2 times faster than the code generated by this code generator. Now, we said, okay, let's see how we do against fully handwritten assembly code. And for this, to the best of our knowledge, the implementation by Emile and Ren is the fastest one. And in the best scenario for us, we get that we are only 13% slower, whereas the worst case scenario, we are 46% slower. Again, this was expected because we know that going directly to the assembly level is the fastest way that we can, or the fastest method is the layer in which we have to write our code to achieve the fastest performance. The implementation by Emil is available here. And well, the thing is that he uses some non-standard calling conventions to avoid certain overhead. So that's what I was saying before, that yeah, we can reach very fast implementations, but then if we need to maybe move this to another platform, if we want to generate code for another prime, maybe it's not extremely straightforward to get other implementations. Now, the second application was the round 2 ski sign verification. For this, the only thing, without entering into details of ski sign, what we need to do is the evaluation of an isogeny. In order for us to evaluate isogenies, we need to apply only operations on the quadratic extension of the finite field. And this layer, arithmetic on the quadratic extension, practically is just calling operations on the base field. So definitely improvements on arithmetic at the base field level will end up having speed ups in the whole of the verification of ski sign. Now, if you take a look at the primes of ski sign, they have a high degree of let's call Montgomery friendliness. So they are good candidates to have application using our library. And then for primes of level 1 and 5, we were able to eliminate a conditional subtraction that is needed in the current implementation or the reference implementation, so that also helped. And when we compare the ARM version of ski sign for verification against the reference provided by the ski sign team, we are 2.3 times faster than the reference implementation. So here we have the numbers reported by the ski sign team in the submission to NIST. These numbers here present our results, and here I would like to mention that even though we already got some really nice improvements, we went a bit further and tweaked a bit by hand the code generated by our generator. I know that this goes a bit against the original idea, which was just to have a generator and to avoid having overhead, but we wanted to get faster results, let's say, and then we went for what we call the custom implementation. Now, the board that we were using to benchmark this is the STM Micronucleo, which is the same board that is used by the PQM4 project to do the benchmarks. And this particular board has 3 banks of RAM memory, which are denoted as RAM 1, 2, and 3. And the size of these banks is 192, 64, and 384 kilobytes, respectively. And it just so happens to be the case that the first bank is faster than the other 2. And then we also realized that the ski sign for verification, mind you, because signing is not available in Cortex M4 yet, but the verification code sits perfectly well on the first bank, meaning on the fast one. Then in order for you to force, let's say, the execution to be happening only in that bank, we just need to do some small configuration, nothing really scary or difficult. So choosing only the first bank, we get these numbers. So you can see that we decrease significantly the time taken, and these numbers here correspond to taking the reference code submitted to NIST and just plugging in our implementation. Cool, so this looks fine, but there's just one last thing. that we tried. And that has to do with how the code is organized in SkiSign, in the reference implementation. So the arithmetic layer consists of two parts, the base finite field and the quadratic extension. So the FP layer is the one that is generated by either generator. The quadratic extension part is a separate file. And then the protocol per se, signature, verification, and key generation, whenever they need to, whenever some arithmetic operation is needed, practically we use operations in the FP2 layer. So having functions here being called in this file, and given the fact that this is what is mainly called outside, then there is a lot of overhead when we want to call a function residing here from inside here. So we said, okay, so we can get rid of this overhead just by making some refactorings, by being smart with how we move things around. So what happens if we merge the two layers? Well, first of all, we can have the problem that our code size can grow, particularly if we inline aggressively. But we did it anyways. We played with it. We were checking in which configuration the code size was growing substantially a lot. And we tried to avoid those cases. And particularly, we noticed that there are some functions that are quite large and not used very often. So we decided just to keep them apart and remove the inlining for these ones. So in the end, we managed to squeeze a bit more of performance, and the growth was mild, was moderate. It was not very bad. I don't have here the numbers when it comes to the size of our implementation, but if you are curious, please take a look at the paper. I reckon that it would be just more important to show the execution time, because remember, that was one of the main goals of this group of brave cryptographers at the beginning of the session. So we are focused on speed of execution here. So these are the final numbers, and these are the ones that we presented in the end in the paper. Well, the other ones are also included, and the table is a bit has more details, but these are the ones that in the end brought us to this to the best performance that we have. Of course, again, the custom one had the caveat that we need to hand tune it somehow, but the one that we can get just from the generator corresponds to this. And this one is the one with the refactor that was applied to both our version and the reference version. All right, so this is all I wanted to say about the arithmetic part for SkiSign and the RFC. So as future work, what we identified is that maybe instead of just focusing more on SkiSign, we can also go back to the RFC 7748, and we can maybe apply the same trick as we did with SkiSign. We can merge the two layers into assembly. Again, this kind of goes against the original idea, which was to have something that requires almost no maintenance to produce new code. We can even go further and also apply the same assembly tweaking on the elliptic curve layer. Maybe also we can take a look at different multiplication strategies like the interleave multiplication or reduction. Another thing that we can do is maybe we can apply the fast multiplication on the quadratic extension level, which is due to Mr. Patrick Longa, who is here in the audience. And I lost it. Oh, there we go. And well, since some of you who have attended some of the previous seminars, particularly the affiliated events, well, it seems that doing formal verification is a thing now, so we can try to extend this and to formally prove that, to formally verify that our implementation is correct using, for instance, the now popular Jasmine language. Okay, I'm more than happy to take any questions you may have. Thank you very much for your attention, and well, thank you for your time.
Thank you, Isaac. Any question for the audience? Don't be shy. No? Okay. So I have one quick question, maybe it's just concerning the applicability. Do you try with other schemes, for example, QFesta, CSI?
That's a very good question, and the answer is no. Literally, in the paper, we specify our targets at the beginning, where the ECDH protocol and SkiSign, particularly SkiSign, was the one that detonated everything. So we were focusing mainly on that. We finished, and we said, okay, we can try to extend it to this very easily. For QFesta, I haven't really, tried to plug them in, but as far as I know, it's just maybe taking the arithmetic and plugging it in. I don't really know how QFest has, what the requirements are for, sizes and whatnot. So I think that maybe we shouldn't have any problems when it comes to using the device, because as I was mentioning before, currently we do not have the signature, particularly because of what Alexander was mentioning before. We need large integers and some libraries that are not readily available for the Cortex-M4, but that is maybe one natural extension to this work. But so far we haven't tried any other isogeny-based or any other elliptic curve-related protocols.
Okay, thank you. So there is one question.
Hi, thank you for the presentation, great work.
Thank
So
you.
I have one question regarding your framework. How easy or difficult is it to extend to other ISS like RISC-V?
That's a good one. I think that it mainly depends on, I dare to say it's not difficult in the sense that what generates the code is just a script. You give us input only the prime, and it checks, if it's Montgomery friendly, if it uses reduction X, Y, and Z, which representation it will use, and everything is self-determined. As I was mentioning before, we have the option of having just a generator that generates or outputs portable code, and that would be super easy to do. You just leave the heavy load to the compiler, and that's it. But if you want to do a generator that focuses on architecture, which is what I understand you ask, then we need to take a look at what instructions we have available that can be not exploited, but leveraged, or that we can leverage to perform faster arithmetic. So in that regard, I think the hard part would be to study very well how the current algorithms that we know perform under those instructions, and then understanding whether there are maybe some instructions that will give or will yield algorithms that we don't know yet that will make the implementation faster. So I dare to say we need to come back like a couple of steps forward, take a look at what we have, take a look at what we have in both in terms of algorithms and instructions, see how they play together. And if they are good, then I would either to say then it's ready to go. If not, then we need to go back to the blackboard and say, hey, how can we leverage from this instruction or that instruction? Take a look as well at the pipeline of the processor, how whether there are whether there is speculative execution or not. So we need to take a look at the architecture per se. Thank you.
Okie dokie. There is no more questions, so I think we can just thank the speaker again.